right? So, different room from yesterday. I don't know whether it's going to be any better today, but I hope so. At least if the computer has any problems, we can easily go into the room and restart it here. So that's an advantage. Right. So the plan for today is we need to continue to do some calculations from yesterday. Okay, because yesterday it kind of it didn't go exactly to plan. It's always difficult when you're trying to do calculations the first time, but I think today we can make some good progress on it. But before we do that, I just want to go through a few minor points about the theory that we haven't addressed up until now. So the first thing is that we mentioned that in the functional there's an exchange correlation part, a part of the functional. And I said the simplest approximation is the LDA, or the homogeneous electron gas approximation to the exchange and correlation. Now, that's not entirely true, because the most simple approximation is no approximation. The most simple approximation is zero. Okay, and if we had a zero exchange correlation in our functional, then what we would in fact have is the Hartree approximation. What I would like is a pen. I don't have it. Looks good. Thank you. So our approximation. So we were saying that the total energy functional in our type of DFT was basically E kinetic, or well, plus E Hartree plus E external plus E exchange correlation. Okay, and so we've written expressions for all three of these parts, and we've written expressions for all three of these parts in a plane wave basis. But the exchange and correlation part, we've just alluded to it. We've said we know the form of the expression, we know where it comes from a homogeneous electron gas, but we haven't really derived it. I don't want to derive it in great detail. I just want to express basically in words and in simple terms where it comes from. Okay? So we said how we apply it. We said if these parts, if the kinetic energy in particular is made from bands or orbitals and is expressed in a basis, then its argument, I haven't really left enough space, but its argument is made up of the set of basis functions in our system. The other parts are made up of the density. There's we'll say that this is based on the density, but in practice it also requires the orbitals. And the exchange correlation we're saying is made up of the density. So the parts that have argument density, we call these density dependent parts. Okay, the parts that do not depend on the density, we call them density independent parts. Okay, or we could say orbital dependent parts or band dependent parts, whatever. But what we need to remember is that if we want our density and we're expressing everything in terms of a non-interacting set of basis functions, then our orbital can also be used to express our density. Okay, so if we just sum over all those orbitals, assuming we have an orthogonal basis set and these have argument r, okay, let's just put that in there. Okay, then we're going to say that that is our density, right? So we can take our orbitals, construct a density, feed it into our density dependent parts, and we can continue around our self-consistency loop and find our ground state energy. Okay, but the question is, we've expressed yesterday how to express these three terms mathematically, but we've only said that this term exists and how we apply it, not where it comes from. All right. So if we look at our density, we say we've got a density out of the system based on this set of orbitals and based on a set of occupancies for each one of them. If we take that density, we can see that that density is expressed. I'll just do everything in 2D. It's easier than drawing it in 3D, right? So what we have is a grid in space, a regular grid, okay? And on that grid, our density changes, okay? So assuming that we've got a point here, in that grid cell, we should have a lot of density. And then as we look at the density surrounding the atomic center, we should have a little bit less. Okay. And so basically we have high density right there, and we have lower density and lower density, and eventually we get to having zero density when we're far enough away from the atomic center. Okay? And what that means is that we can take a piece of our density, because it's expressed on this grid, it's discretized. We can take that piece and we can ask the question, how much density do we have? What is the numeric, what is the number that tells us what is the density in units of density, right? So if we have electrons, we're going to say we're going to have charge density, okay? So we're going to have whatever our unit of charge is, but probably electrons per cubic angstrom. So we'll express that in units of, right? So we'll say, what is that X density in units of density, right? So we'll take X, and X could represent this point, or this point, or this point, or this point. But what we need to do is take that X, and we need to create a homogeneous electron gas with X density, okay? And X density is homogeneous, so it's the same everywhere in the cell. That's supposed to be the same everywhere. And it matches whatever X is here. So if X is here, okay, that has the same density as that point, okay? If X is here, then of course it's much denser, but X must match this point, okay? So we construct a homogeneous electron gas for exactly the density within that point, okay? And once we've done that, we need an expression which will give us the energy, the exchange and correlation energy of a homogeneous electron gas at X. So we sum over all points, over all space. Okay, I suppose we could say over all X, but we'll say X has an R index. Okay, so we'll sum over all space, and what we'll do is we'll say whatever our energy exchange correlation of the homogeneous electron gas, so I'll put that here as well, right, at X, right? So we're summing over, and X has an R index, okay? So we're summing over the density, okay, and we're asking what is the question of a homogeneous electron gas with density X, okay? And we're summing over all possible X's, all right? And that will give us the exchange correlation of our total system. Okay, but the question is, how do we get that exchange correlation? So that's what we said yesterday about the exchange correlation, but we can briefly go through how we achieve the homogeneous electron gas exchange and correlation, and that will be the final piece of the puzzle in terms of expressing a basic DFT Hamiltonian. Okay. Then the plan is, after we've gone through a couple of derivations today, tomorrow we will we'll do two things. tomorrow we will look at more advanced calculations, not in great detail, but we'll explain briefly and simply how more advanced techniques work and why we use them and how they're achieved. But we will also go through the kind of computer aspect of DFT and how we program these kinds of things. Okay, so we've really looked at it in three zooms, in three zoom levels. Okay, so we've zoomed in very closely and we've looked at the mathematics of it, how various parts are derived. Okay, so there's the mathematical part. We've looked at the kind of calculation aspect, which is how we apply DFT and other quantum techniques to solve problems in the real world, and we'll do more of that today. But in the middle is how do you take the mathematics and apply it on a computer in order to get the result that you need to match with experiment. Okay, and that's what we'll look at tomorrow. Okay, so the exchange and correlation, I think I'm just going to go through in the notes here. It's easier than going through lots of slides. If I just scroll on the notes, it's actually a little easier to see because you can see everything at the same time. All right. So if we just express the exact exchange expression, okay? So the exact exchange expression from Hartree-Fock, what we have is an expression that looks a bit like that. All right. Okay, I'll stick. So we have an expression that looks a bit like this. So what you'll see is we have a 1 over r, okay, and this part, the 1 over r and the orbital looks very, very similar to the Hartree expression, okay? The only difference is that the j and the I index are the other way around compared with the Hartree, okay? Why are they the other way around? Because what we're expressing is exchange. The indices have been exchanged, okay? And what we said yesterday was when you take the indices of a Hamiltonian and exchange two of them, what you get is the negative sign of that wave function, okay? When you take the wave function, exchange two indices, it flips the sign of the wave function. And what that is exchange, electronic exchange, or fermionic exchange more generally, because we're dealing with fermionic particles that they're indistinguishable fermionic particles, spin half particles, okay? So this is what happens, and so this is the expression we get in Hartree-Fock, okay? Firstly, I think a good question might be, why don't we just use the Hartree-Fock expression in DFT? Okay, why don't we just use it? Well, you know, why do we approximate the exchange and correlation? Why don't we just apply the Hartree-Fock exchange? Because we know what exchange is, right? We can calculate it. Why don't we just use it? And the answer is, there's two answers. Okay, the first answer is, well, we could do. Okay, that's what's known as a hybrid functional. Okay, and the other answer is, we don't do it because it costs time and computer resources. Okay, it's more expensive to run a hybrid calculation, to run exact exchange, as it's called, than it is to run an approximation for exchange. Okay, so you can do it, and there's certain situations where it's a good idea to do it, and situations when it's a bad idea to do it, but it will be slower than not doing exact exchange. All right, so that's exact exchange. So how do we get from exact exchange to the approximation for exchange from the homogeneous electron gas that we usually use in semi-local DFT, like LDA, GGA, so PBE, BLIP, or BLYP, whatever you want to call it, and meta-GGA functionals like, I don't know, the scan zero functional, whatever, RScan. So the answer is, well, firstly, we set up a homogeneous electron gas. So we set up a space which has the same electron density everywhere in space. Okay, so homogeneous electron gas. Then we expand that homogeneous electron gas in terms of plane waves. Okay, so yesterday we mentioned a lot about plane waves as we were trying to derive or at least express all of these other terms in plane waves. Now we have an easier task. So now we have a constant in space, constant density, and we need to express a constant in plane waves. Okay, so you can think of that like if I have a constant and I need to Fourier transform the constant. Okay, so you think of a Fourier transform, all we're doing is we're saying if we have an integral and we have our function of, well, let's do it in 1D, right? Function e to the I kx in 1D dx, right? This is our Fourier transform. If we Fourier transform that function, what we get is the Fourier transform. So we get in k space of that function. However, if we were to discretize this and write it on a computer, so we have a sum instead of an integral, what we're going to end up with is instead a set of coefficients multiplying our plane waves. Okay, so our plane waves have a frequency index, okay, and we've discretized frequency space into our lowest frequency plane wave, then the next harmonic, right, then the next harmonic, then the next harmonic, and as we sum them together with a coefficient, pre-multiplying them, we get this sum of plane waves multiplied, this linear combination of plane waves, we eventually recover an approximation to our original function. Right? However, this is easy because our original function is in fact a constant, right? It's a constant. So our function f of x just equals x, right? Which is our density, and x is just a constant. Okay. So how do you Fourier transform a constant? Right? The same as any function, right? You just sum up the states in such a way that you get a flat constant, a homogeneous density, right? And so if you do that and you express this exchange integral in terms of plane waves, you write the density in this way. So, we said the density is written like this, but we could also write it like this if our states are orthogonal. Okay, we get an exchange integral like this. We Fourier transform the Coulomb part, the 1 over r part, okay, which just looks like this. We went through this yesterday, the Hartree potential. So that is the part of the Hartree potential which comes out of the Fourier transform, the so-called operator, right? And if we put that together, okay, our exchange integral in momentum space and our Coulomb part together, what we get is something that looks a bit like this, right? We get something a bit like that. And what we find is, because you can see we've got our plane waves here, right? We've got two separate integrals. Okay, we've got an integral over plane waves in space, integral over plane waves in space, right? And we can just analytically integrate those integrals. Okay, we can analytically integrate them. And what we get if we integrate them analytically is delta functions. Why do we get delta functions? Because we've got orthogonal states. These plane waves are orthogonal to each other. This plane wave is orthogonal to this plane wave. Okay? Every other plane wave is orthogonal to every other plane wave. And so because of that, we have an orthogonality relation out of our integral. And in fact, all we have is constant multiplying a delta function. Okay? And if we just multiply that constant together, we get this deal, okay, with a couple of delta functions. And we've just got one last integral to do. Our delta function we're going to say is 0. Why do we say our delta function is 0? Well, because they're orthogonal, right? And once we go through these very simple integrals, right, you can see that these are trivial integrals, right? once we go through integral of 4 pi, okay, over all space, because they're constant, right? Eventually, what we get out as our exchange integral is minus 4/3 3 over pi to the power of a third, okay, multiplied by the electron charge squared. Okay, so we said electron charge squared, right, multiplied by the cube root of the density. Okay, so in the end, this term, at least in the LDA approximation, or the homogeneous electron gas approximation, becomes very easy, right? All we have to do is take our density, right? Take it to the cube root, the power of 1 over a third. That's our density, okay? And multiply by this, which is a constant, okay? It's a constant in space. We just take our density, multiply it by a constant, and we get an approximation for the exchange. It's easy. Right. We'll skip over the Fermi wave vector, but know that this is a thing that we can calculate like this. Okay, it's just the Fermi wave vector is just a function of the density. Okay, all right, function of the density. And so now we can take that function of the density and we can use it to express the correlation part. Okay, so this is the very, very last part of the functional, the DFT functional, the correlation part. And we said yesterday that if we want to express the correlation part of the functional, we need to go beyond Hartree-Fock. Okay, because if we just cover up the correlation part and run kinetic energy, Hartree, external, and exchange, that is Hartree-Fock, right? And the definition of correlation is the difference between Hartree-Fock and real quantum mechanics, reality. Okay, so if the difference between Hartree-Fock and reality, so the difference between the energy we recover from Hartree-Fock, right, and reality, so we're going to call that quantum mechanics, or the Schrödinger equation if we could solve it, the many-body Schrödinger equation, right? That is defined as the correlation energy, right? So it's the difference between Hartree-Fock and quantum mechanics. So in order to calculate that, what we need is something beyond Hartree-Fock. Ideally, we would use quantum mechanics, solving the many-body Schrödinger equation, but unfortunately, well, we can't do that because of what we said yesterday, and also if we could do that, we wouldn't need to bother with any of this. We would just solve it, right? However, what we can do is use approximations which are better than Hartree-Fock, right, in some way, and use those approximations to give us a guess for the real quantum mechanical result, and then look at the difference between that and Hartree-Fock and use that difference to give us an approximation for the correlation. Okay, so RPA is an approximation beyond Hartree-Fock. RPA is an approximation to plasmons, I guess you could say, and it's expensive. Right? So if I wanted to do an RPA calculation on a computer, I wanted to do an RPA calculation on a computer, it would take a lot of time, it would take a lot of computer resources, and I could only do a small calculation. Okay, and you can think of this like a ladder. Okay, when you start at the bottom of the ladder, it's all your calculations are quick, all your calculations can have many atoms, all your calculations can run on a small computer. As you go up the ladder, your calculations get slower, the size of the system, the number of atoms you can run gets smaller, and also the size of the computer you need to run it gets bigger. Okay, and so we have DFT at the bottom, then we have Hartree-Fock. You could argue Hartree-Fock is not as accurate as DFT, but it's definitely more expensive than DFT. And then you have RPA probably on top of that, and maybe GW theory, coupled cluster, etc. as you go up the ladder. Why is RPA expensive? RPA is expensive because in order to get a converged result in RPA, you need to consider all of the excited states, all of the excitations in your Hamiltonian. Okay, in DFT and Hartree-Fock, you can just truncate at the chemical potential if you have an insulator, and a few conduction states if you're doing a metal, right? And then you just stop and ignore all of the rest of the excited states. In RPA, formally, you need to deal with all of the excited states. So it's very expensive because it adds a huge amount. If you think of your Hilbert space of, starting at 0, going up to infinity, okay, these are all my states. I'm going to say that part is my valence electrons, right? And then all of these states are just conduction electrons. If I wanted to do a conduction calculation or an excited state calculation, I would need to worry about these states. But in a normal ground state DFT calculation, I just have a very, very tiny fraction of the Hilbert space that I need to consider, right? In RPA, that's not the case. I would need to consider all of the states, or at least a very, very large number of states, okay? So what we can do is we can say, well, okay, RPA is very expensive. I don't want to do an RPA calculation, but I can do an RPA calculation of the homogeneous electron gas, the same way we did with the exchange calculation of the homogeneous electron gas. And if I do that, do I get another simple expression like I got for the exchange? Okay, so the exchange gave us that expression. What happens if we do, if we apply RPA? Okay, I should say what RPA stands for. RPA stands for the random phase approximation, but it's a very bad name. It doesn't really express what it is. But if I get that, I get an approximation to this, well, now I should be able to get an approximation to the correlation energy. All right. So the advantage we have is that the homogeneous electron gas expression for the RPA has a simplified not approximation, it's exact, but it's much simpler, okay? Effectively, we only have to deal with a diagonal matrix, okay? So if you think of RPA as being, it's supposed to be a matrix, right? A matrix. If we have a Q by Q, right, matrix, when we're just dealing with the homogeneous electron gas, we can only consider the diagonal part, and of course, off diagonal is 0, okay? So what we get is known as the Lindhard function, okay? And the Lindhard function looks a bit like this. It's quite easy to calculate. So last year with a student, I calculated, we derived an expression for the Lindhard function, and the student programmed it in, I think, 3 weeks, from start to finish. And we implemented it in CASTEP. Did some calculations with it. It's quite easy to do, right? So it looks like a big expression, but all we've got is the difference between the Fermi-Dirac distribution at 2 energies. And so, of course, we know that the Fermi-Dirac distribution looks like that, right? It's that function, the 1 over 1 plus e to the e minus mu over t. So we've got a difference between Fermi-Dirac distributions. And then the whole thing is just divided by a frequency plus an energy plus the other energy plus a small constant to keep the whole thing deterministic, causal. Okay. So trust me, we can. I don't think there's any point deriving it. Just trust that this is easy to calculate. It really is. It's not a complicated expression. And if we can calculate the Lindhard function, that allows us to calculate the dielectric polarizability. That's what that is, the dielectric polarizability. And that approximation for the dielectric polarizability allows us to calculate the RPA in this way, right? And so this way, the way we calculate the RPA, like this, is known as the adiabatic connection, okay? So that is the adiabatic connection, right? So basically we're saying that this is the true result, this is our approximate result, and we're saying these are connected through, how can you say it? They are, I can't think of the word really, but let me say it. They're connected in space, I think is the way to say it, right? So by connected, I mean that you could have a path from here to here in a state space, right? We could go from this result to this result, and we could say we could have. So we're saying that this result is correct, and this result is approximate. Okay, and so somewhere along the path in space from approximate to exact is a bit more exact, a bit more exact, a bit more exact, until we have exact, right? So that connection, that adiabatic connection in space, just expresses the connectivity between approximation and exact result, okay? And so if we look at the approximation, sorry, if we look at the connection and the expression for RPA, it looks like this. And so all we've got to do, calculate the Lindhard function, okay? Stick the Lindhard function into the dielectric function to give us, so Lindhard function gives us polarizability, okay? Dielectric function gives us dielectric from the polarizability, and then dielectric goes into the expression for the RPA, and that eventually gives us the energy per electron, okay? And what we can do with that is take limits, okay? So we can say the Lindhard function or the RPA of our homogeneous electron gas, you know, we can say we know what the result is at low density, we know what the result is at high density, and we can write a spline, okay, or an approximation which connects low density to high density, and we can have a whole expression which gives us blah, 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 this, okay, right? So eventually we get an expression which is simple, okay? It's simple. So you might be asking, what is RS? And I think I've got it written down here, but well, it doesn't matter. It's a radius associated with the density. Okay, so effectively we put the density into this expression, simple expression, and we get an expression for the correlation energy, okay, in the LDA approximation. So that gives us two expressions for exchange and correlation. When added together, give us the whole expression for LDA DFT. All right, and I think that's 44. Okay, we started a little bit late, but it's kind of a brief whistle-stop tour of pointing at things in DFT and saying, you know, what it is. Okay, we can't really go through mathematically and say this is this. We don't have a lot of time in this course, but we can at least look at all of the things and try to understand them from a high-level point of view. Okay, so that's the end of DFT as as a mathematical tour. Yeah, I think that's what I want to call it. What we've done is a mathematical tour of DFT. We haven't done a set of derivations. We haven't been rigorous about deriving every single thing. We didn't have enough time to do that. But what we have done is we've had a tour of DFT, like a sightseeing tour. This is what this is, this is what this is, this is what this is. And that should allow you to read about it on your own, or to go to a longer course where these things are derived in greater detail. Okay? So the last thing we're going to do today before we do some calculations is to look at some problems with DFT. Okay? And what I hope is that we can go through some problems in 15 minutes, I think. So we'll go through the problems in about 15 minutes, maybe 20 minutes, have a quick break, and then we'll go to do some calculations. Okay? Right. So the first problem that we encounter in DFT is the band gaps are terrible. Okay, particularly in semi-local functionals like LDA. Okay, so you do an LDA calculation and you get something like this, right? So, so where do I want to start with this? So one thing I might do is switch to another presentation. So I wanted to look in the notes when it came to the derivation of the LDA exchange and correlation, but I think maybe we'll look at another presentation with some pictures in it. Maybe. Does it have the pictures we want is the question. Yeah. Yeah. Right. So the question is, I guess the question is, why do we do DFT? We've said this many times. We do DFT because we know it's accurate enough for many purposes, and it's fast enough that we don't need to be waiting half a year for our calculation to finish, right? But it's not accurate for many purposes, and one of those purposes is band gaps. Okay, I don't know whether I need to use this presentation because I can just, it's just difficult to decide which one I want to use. Okay, so what we need to say is that DFT and Hartree-Fock are both inaccurate when it comes to band gaps, right? And they're inaccurate with opposite sign. Okay, so LDA and other semi-local functionals will underestimate our band gap, whereas Hartree-Fock will overestimate our band gap. Okay, so the question we have to ask is, can we do better? And the answer is, of course, we can do better. And we can do better in a very simple way. So this is what a hybrid functional is. If Hartree-Fock is giving us a result somewhere here, and LDA is giving us a result somewhere here, the obvious solution to the problem of band gaps that should be on the line, right, is to do a linear combination of LDA and Hartree-Fock and try to land on the line somewhere, right? It's kind of magic, right? You see what you want and try to achieve it. And what you can see is if you take a hybrid functional, in this case, I think we're looking at HSE, which is a kind of approximation to the PBE0 functional. We can make it lie exactly on the line, okay, for a wide range of oxides, insulators, systems of interest. Okay. Right. So there's the expression for PBE0. Okay, and you can see what we're actually doing here is we're taking PBE exchange, which is our exchange approximation. This part, we're taking the PBE part. Okay, taking three quarters PBE, 1/4 Hartree-Fock exchange. Okay, summing them together, and now we have this sort of magic exchange functional. Okay, and so the idea is effectively, if we have some exact exchange, some Hartree-Fock exchange in our approximation of exchange, we will do better. Okay, so just this is all we need to know. All we need to know is if we have LDA is not very good, Hartree-Fock is not very good, but if we sum them together with some coefficients, we will lie on the line. That's all it is. There's nothing more complicated than that to a hybrid. Okay, it's simple. Okay, and we do it, and we get something like this, and we do lie on the line. Right. So, okay, a couple of things to mention. A lot of people in published work use functionals like B3-LYP, B3-LYP. Okay, it's a hybrid functional. For physics, for solid state, for material science problems, it's a very poor choice. okay, it will give you bad results, or worse results than you can get with other functionals. Okay, if you think that you need to use a hybrid functional, a better choice would be something like PBE0 or HSE. Okay, so that would be PBE0, right? So we're talking not PBE, which is a semi-local GGA functional, but PBE0, which is the hybrid version, which is expressed like this, right? A bit of Hartree-Fock exchange. And HSE is an approximation to PBE0, which is easier to calculate with a plane wave basis. Okay, so either of those would be adequate for the solid state problem. But we should ask the question, why are band gaps so poor in LDA? Why are band gaps so poor in semi-local DFT? And the reason is mainly self-interaction error. Okay, so this is the last thing I'm going to speak about before we do something. Okay, this is not very good. Just need a little bit of space here. All right. So if we go back to the expression we had for the exchange, okay, and we just copy it out. So if I just take exchange as, what am I going to write it as? E squared over 2, right, sum over ij, the integral, and what are our integrals? So we actually got a double integral. Missed an integral there. We've got I star j star, and then we've got a 1 over r minus r prime. Okay. All right, something like that. Something like that. What we noticed is, okay, let's just put vectors on that. Right, what we notice is we've got ij, ji. Okay, so let's put those in, right? But let's also copy this whole thing out underneath. Copy the whole thing out. With the indices the other way around. Okay. Whatever. All right, and so that is just another way of writing that term, the Hartree term. Okay, so how can I convince you of that? Well, let's look at the density. So we know that the density is just okay. You might be asking, well, why have I got I and J? Well, if we have a non-orthogonal basis set, we could have both indices. Okay, so let's just say that that's our density, or how did we write it yesterday? We wrote it as n yesterday. All right, so we've got our density like that. So in this case, what we can do is we can say, well, we've got a j there, we've got an I there, so we can take these two terms out. All right, get a density, we've got an I there, we've got a j there. Just split the indices, we can take a density out. So that and that will result in us having n of r over r minus r primed integral whatever dr. Okay, and that's going to be equal to our Hartree energy, right? So we can do that, right? That's that part. But what we should do is we should say, what happens if we're looking at just one electron? Okay. What happens if we're just looking at one electron with itself? Okay. So what I'm going to do is I'm going to say, well, now I and J. Okay. Firstly, I should say these have also got a position index, right? So we've got an R and an alpha. An R and alpha. Which way around is it? I always get this wrong. R and alpha. Okay, R and alpha. Right. So if we look at the density, R and alpha. Okay, R and R. Okay, if I've got wave function I of R and wave function J of R, same position index. Okay, and I look here, wave function J star of R primed, wave function J of R. Okay, that density is that's that expression. Now, if I've got wave function J star and wave function I of R not star, that's not our density, right? So, however, if I decide that I'm going to make all of my indices J, right? So now I'm just looking at one particle, right? Just looking at one particle with itself, yeah. So this represents a particle index or a state index. It represents an orbital. It represents a band. Okay. So if I just say I'm looking at one electron with itself, okay, so J with J, what you can see, hopefully, is that these are identical. Right? So if this is J, 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 they're all J, right? It's identical. Right? And so the exchange and the Hartree will cancel if you have one particle with itself. If you're just looking at the interaction of one particle with itself, it will cancel. Okay? So in DFT, if we have the Hartree part, which is equal to this, and we're just looking at one electron with itself, this does not cancel with the approximation for exchange that we calculate over here. Okay? So if we don't calculate the exchange using Hartree-Fock exchange like this, for one particle, the Hartree interaction does not cancel with the exchange. Okay? It should, right? Because a particle should not interact with itself, right? This should cancel. The exchange and the Hartree energy should cancel with each other for one particle, right? And the consequence of them not cancelling with each other, is so-called self-interaction error, right? Self-interaction error, the consequence of self-interaction error is that an electron can electrostatically interact with itself. It can electrostatically feel itself, right? So if you imagine, I don't know, if we have an atom, okay, and we have some electron density around the atom, surrounding the atom, and it has some distribution in space, which we're expecting, right? Electrons are negative, and itself is negative. So if you imagine it's interacting with itself, negative self interacting with its negative self, it's going to push itself away from itself. It's going to be more widely distributed in space. Okay? It's going to be pushed apart from itself. Right? That is self-interaction. Okay? And so this happens predominantly in heavy elements. So if you think about transition metal oxides, okay, so for example, copper oxide or titanium oxide, right? Titanium. So you could have I don't know, platinum, but more commonly we might be looking at something like titanium oxide, or you could look at basically any of the transition metals interacting with oxygen. You're going to experience self-interaction error in a semi-local DFT functional. Okay, and what that means is, if we imagine we've got, say, titanium and oxygen, right, in our lattice, in our crystal lattice, right? You imagine the D states of titanium, the D states. So we can draw something that looks a bit like a D state, right? The D states around the titanium, they are quite localized. They should be quite localized, right? Whereas you would expect that the P states of oxygen would be sort of more spread out in space relative to the size of the atom. Problem is, if we have self-interaction error and the electrons are pushing themselves away from each other, okay, the should be localized D states of the titanium will be pushed to be more delocalized in space. They're pushed to be more delocalized. And what that means is now we get a significant overlap between the oxygen P states and the titanium D states. Okay? And that significant overlap results in a closing of the band gap. Right? You think, if my atom's electrons are overlapping, the D states are overlapping with the P states, and I have a sort of continuous electron band in the system, what does that resemble? It resembles a metal, right? So it's becoming closer to having a conduction band, right? So what happens is you model titanium oxide with LDA, for example. You get self-interaction error on the D states. You get electrons pushing away from each other, becoming over-delocalized, and it spuriously predicts that the oxide transition metal, titanium oxide, is a metal, which of course is completely wrong. What we need is a way to make our D states relocalized. We need to make them localized so that they do not interact so strongly with the P states of the oxygen and do not form a metal band in space. Okay? Because it's not a metal, it's an oxide, right? And so basically there's two ways to fix this problem. You can use a hybrid functional, and a hybrid works because we're putting in some exact exchange, and part of that exact exchange is cancelling out the self-interaction, which is coming directly from the non-cancelled Hartree term. Okay, so it makes sense because we're trying to make the band gap better, and so the band gap is problematic, is too small because we have self-interaction. Fix it by adding some exact exchange, use a hybrid functional. Okay, but that's expensive. Takes a lot of computer resources to do that. The alternative is we use something called LDA plus U, where U is the Hubbard model. Okay, and this is very closely related to exchange, but it's an approximation for it, and we might talk about that tomorrow. But LDA plus U or a hybrid functional both result in lower delocalization and better band gaps, but not perfect band gaps. Right, I think that's enough, sort of theory speaking, for today. Of course, there's always more, right? But I think what we'll do is we'll have a short break, and then we will come back to looking at some calculations. So if you want to take a break, and we'll come back to it, say in 10 minutes.